Bueno. Esta tarde, ¿eh? ¿O cuál? Sí, sí. Puedo presentar. ¿Sí va? ¿Se lo puede poner allá? Mejor eso. La derecha, izquierda y la. Ok. Bueno, ¿listo, Mark?
Yeah. Okay, let's begin with the next talk. I'm very happy to introduce Professor Christopher Stephens. He's a professor at the Institute of Nuclear Sciences in the university, but he is also affiliated to the Center for Complexity Sciences. And I should mention that he is one of the main founders of the center. So please.
Thanks, Max. Yeah, it's. I wish I wasn't here in the sense of up here, because originally we had planned a talk by Per Sodersten, who's a very well-known neuroscientist at the Karolinska Institute in Sweden, but unfortunately, due to health reasons, he couldn't come. So I'm gonna fill it in. So hopefully, it won't be too. My talk won't be so much worse than his. You won't have seen his, so you won't have anything to judge by. I had no idea that Philippe would be talking about exactly the same thing that I'm talking about, except that he was talking about the conductome in the context of E. coli, and I'll be talking about it in the context of human beings. Though essentially, I think, as you know, I'll go pushing this concept. I think that's what exactly you're trying to do in terms of your experiments with E. coli. So the thing is that I'll talk a little bit about this concept, the human conductome, and basically it's to do with the idea of, you know, why do we make bad decisions? Obviously, the question is, what's a bad decision? But the thing is, I want to start off, first of all, I loved Hernan's little thing yesterday about Borges, one of my favorite things in literature. So here's another favorite thing. Who's ever seen The Hitchhiker's Guide to the Galaxy? Anybody? Well, obviously the British people in the audience. So the thing is that in this book, you know, the most advanced civilizations on the planet get together to try and, because they're fed up with trying to study the question of, you know, why life, why the universe, why God, why everything, right? And so the thing is, they get together and they program a computer, they're basically called deep thought, to try and just come up with this question. Come up with the answer to this question. You know, obviously all the theologians, philosophers, etc., were scandalized completely, because, you know, what are you going to do once all of this has been answered? And the thing is that this computer basically was going for thousands and thousands of years, through one generation, another generation, and eventually all the descendants of these different civilizations were there ready and waiting for when the computer came up with its answer, right? And the thing is, the computer, with a very depressive voice, said that nobody was going to like the answer. And the thing is that obviously people were, well, we've been waiting so long, we don't care, we want to know, we're on tenterhooks, we'd like to know what the answer is. Computer insisted that he didn't really want to give the answer because it was going to be very disappointing, but anyway. So what was the answer to the ultimate question about life, the universe, and everything? It was basically that, 42. So that's why everybody was, why the computer thought everybody was going to be disappointed, because what does it tell you? That the answer is 42. And the computer to tell them, well, the thing is they would understand what 42 meant if they could understand in a deeper way the actual meaning of the question. And they need a much better computer than he was to be able to do that. And so they set about trying to make that computer. So here what I want to show, this is my 42, right? So basically, this is a predictive model for predicting with obesity based on about 2,500 variables that I have on populations that I have here in the UNAM. And I'll show you very briefly, basically the range of variables that I'm using. And the thing is that, you get actually, very good predictions in one sense. But the thing is that it's 42 because I have no idea, basically, in some sense, how to disentangle causal relationships and understand them in a deeper fashion as direct, indirect factors, proxy factors among those 2,500 variables. And that's going to be, so you think you have a challenge with the E. coli. I would say that this is many orders of magnitude, but conceptually it's the same. And I like the idea of at least understanding, let's call it the genotype to conductor type map, as opposed to genotype-phenotype map. So this is my 42. It's a predictive model for obesity, and basically comes from this. So the thing is that essentially, we have a population, well, we have many more than that, but the present results are on this population of 1,076 academics, non-academics from the UNAM, where we have about 2,500 variables ranging from the genetic, epidemiological, physiological, now we're putting in psychological, et cetera, anthropometric. And in what we could call the epidemiological, there are many, many different sub-categories. And basically, this is the results of that model in terms of performance from a machine learning point of view. So what we're doing is taking those 2,500 variables and just shoving them into this machine learning algorithm and saying what comes out is saying who is obese, who isn't obese. Okay, so the thing is that basically all I'm doing here is just showing there are many variables, right? So in other words, we go from personal data, basically things like your job, where you live, et cetera, to anthropometric variables, to social variables, basically how many friends have you got, what's your friend's age group, et cetera. Basically, any health problems that you have, basically your personal health history, what you know. Basically, here one will see in a second, one of the questions we asked that might sound a bit strange is how many calories is there in a glass of water? And you find that actually that's very predictive of obesity. Obviously, trying to understand why is a different question. No, we interviewed the people, but so there was a questionnaire, but the thing is that it was one-on-one, right? So then the thing is that we had a reasonably ample spectrum of physiological blood variables, cholesterol, insulin, hemoglobin, triglyceride, et cetera. And then basically questionnaire about how they felt physically, what did they think, perception questions, self-perception questions. So the thing is, I'm just going to go through a couple of things to basically try and emphasize what the challenge is. So the thing is, what would be great if you had 2,500 variables and 3 were important. All you were doing was running the computer to find which of the 3 of the 2,500 variables were relevant. Unfortunately, life isn't so simple. The thing is that not only do you have to disentangle trying to develop an understanding of the relationship between these variables, what you find is there's just many, many, many variables that are relevant. So the thing is that he is one that's from the point of view of, let's call it public health of the workers of the UNAM, this is an extremely important one because what it's telling us is that academics have an obesity rate of 14%. And basically, many of the, basically for the workers, let's call it, it's close to 40%. It's between 35 and 40%. So we're not just talking about a bit more or a bit less. It's a question of academics have 3 times almost less obesity rate than non-academics. Obviously, this is an enormous challenge to go, well, It'd been lovely if we could just turn everybody into an academic. What do you give them? A piece of paper saying, welcome to being an academic in the UNAM, and things would turn around. This is a proxy for something. Well, it's more than something. It's a proxy for many, many, many things. And part of the conductome in that sense is trying to determine essentially how that relates to behavior, but what it is in behaviors that this is being a proxy for. So this is just a little bit of a potpourri. Obviously, age is an important factor. So here's one of my favorite ones, is like short people have an extremely higher tendency to be obese, in the sense of body mass index bigger than 30. And the thing is, I'll go through why that is, or why we believe it is from the point of view of hypotheses. Here, in the sense of, this is what we standardly know, almost any ailment you can imagine, there's a higher frequency for finding it among the obese than the non-obese. Here shows that for instance, here, the frequency of obesity is very much correlated to how many friends you have. Right? What's cause and what's effect there is, once again, a different matter. It depends on, it's related to your social circle, in the sense of what's, how are your friends in that sense. The other thing is that it's very much associated with bad health from the point of view of how do you feel about your health. One of the interesting things here is basically, we ask, what would you like to do about your weight, right? And basically, what that's saying is that almost 98% of people with an obese BMI would like to lose weight. But then what you find is that, what do you think about your actual weight? Well, the point is that what that says is about 70% are quite happy, and 30% are very happy about their weight. So the thing is, there's an incredible disjuncture there between one sense what they'd like, and another thing is what do they think about themselves. And the thing is that this is something that's very much associated with how deep the conductome is, in the sense of trying to understand why we think the way we do and why we do the things that we do. That's the health knowledge one. And also, we try to reconstruct histories by asking, questions about how they were last year, 5 years, et cetera, and there's many, many interesting things that come out of that too. So the thing is that what I want is a prediction model. Obviously, you can imagine, a prediction model is very important from a public health point of view, but more than that, basically what I would say is the principal purpose of all living things is to predict, right? In some sense, that's the thing about E. coli. E. coli is, in one sense, got prediction models about what to do in a certain environment. In that sense, how much filament to produce, how much basal part of the flagellum to produce, et cetera. And basically, why do we want to predict? Because we use prediction models to essentially take decisions, and a decision is associated with an action. So what are some important decisions? Well, obviously, that's one, that's another, that's another, that's another. And the thing is that this idea of the conductome, in some sense, is a conductome for every single decision that we're taking, in the sense of what influence a particular factor has for a particular action that we take. But the thing is that you can go and put the concept of a decision beyond what we would naively think from an anthropomorphic point of view, and say, well, from an evolutionary point of view, at the population level, well, as we'll see, cats or pre-cats, not being familiar with the evolutionary history of felines, that there would have been some cats, probably millions of years ago, that didn't actually turn over when they were falling from a tree, and therefore would receive brain damage at a higher rate than the ones that did turn over. And in some sense, that's a decision, if you will, at the level of at the population level. In that sense, that's what evolution is doing, basically choosing those evolutionary paths that make, let's call it, the better decision. And, in that sense, I think even getting down to the level of something like a lac-operon, in one sense, it's making a decision, not a conscious decision in the way we think of it, but in a sense of choosing between alternatives. So there again, there are good decisions and there are bad ones. And the thing is that whether it's good or bad is obviously going to be completely context dependent, meaning it depends on the environment and the behaviors you may adopt in that environment. Absolutely, completely, yes. Yeah, absolutely. What's good today is not what was good 100,000 years ago is not necessarily good now, or vice versa. So thinking about what a decision is, it's a selection between alternatives implying a change of state. And you can look at it at the individual level, the collective level, even at the evolutionary level. And it's associated with an action, not a thing, and it's associated with a behavior or a strategy. In that sense, I'd like to think of a behavior as really being, in some sense, a tendency, meaning a correlated sequence of decisions or actions. We don't tend to think of a behavior as just a one-off. We tend to think of a behavior as something that's correlated in time, in a sense of modeling the response of the system to a particular environment that comes up time and time again. But there are key questions there. This is absolutely fundamental. How do you even begin to enumerate the alternatives? Right? So that's the question in the sense of what are the behaviors that an E. coli can exhibit? How do you come up with the conductor type, meaning what is the range of behaviors? The thing is that rock, paper, scissors, you know, in the sense of game theory, is not an adequate framework for thinking along the lines of what the conductor type is, I don't think. And then the other key question is, how do you weight the alternatives in the sense of the factors that contribute to you actually having a particular behavior? So the thing is that, you know, I'll go through, sometimes when I give talks more to the humanities, I would say, then the thing is that it's extremely interesting just to find what people's intuition is about the physical world versus, let's call it, the non-physical world, from the point of view of how we take information and basically how do we make decisions. And the thing is that, you know, I'm sure nobody here would get this inverted commas wrong. But what I'm going to show is the following. So, you know, I'll ask a question in the sense of, well, the dumb question. You know, if I drop an object, what happens? Well, you know, it's like then my prediction model, in the sense of can I predict what people are going to predict, is basically say that I predict that 100% would have said, well, it drops to the floor. And that's inevitably what you find. Interestingly, if you say I drop two objects of different masses at the same time, which is the floor first, again, in an audience like this, I presume nobody's going to get it wrong. You will be amazingly surprised when you talk to a humanities audience how many other than both at the same time. And the thing is that this, you know, when I first did it, was a slap on the face for going, well, you know, this is not quite in our decision-making apparatus because it's not everyday experience, right? So the thing is that basically trying to predict what people are going to predict is in some sense a simple task, and in some sense it's a complex task. Here I thought it was a simple task even for just these basic physical phenomena, and it turns out that it's not quite so easy, because the thing is that our decision making or our predictive models from this point of view essentially come from everyday experience. And everyday experience isn't about dropping two objects of different masses at the same time. It took a Galileo to do that. But the thing is that you can also go in the sense of decision making at a level other than experience of the physical world. You know, so the thing is, you could ask, well, you haven't drunk any liquids in 3 days, and someone gives you the offer of a liter of water or a box of cornflakes. Which would you choose? Well, once again, it doesn't take the genius, you know, everybody's going to go, you know, water, please, not cornflakes. Same with the thing of, you know, if there was a fire here suddenly, what would you do? Run for the exit, or, you know, keep listening to me and we'd all go down in flames together? Once again, you know, the thing is that I can predict what people's decision making is going to do. The same in the sense of, you know, what would you rather have? Unless you're a strict vegan, if you had a choice between enchiladas suizas, frijoles, and carnitas versus almost 8 kilos of celery, I think, well, it might not be 100%, but it'd be very close, right? So now the thing is, though, we can all intuit why there's a clear response for one option versus the other. But if we get down to you haven't drank water or any liquid in 3 days and someone offers you a litre of Coca-Cola versus a litre of Pepsi, which do you choose? Well, am I going to be able to predict as well there, right? So the thing is that, well, we can do it. I mean, the thing is that's the only options. You can't go, I hate soft drinks, right? It's either one or the other. So who would choose Coca-Cola? Okay, who would choose Pepsi? Well, no, there's no vergüenza, no? There's no shame in choosing Pepsi, right? I'm not like you almost had a hand up, Javier. Okay, I didn't. So the thing is that I put 70 and 30 because that's what the net sales of Coke and Pepsi is in Mexico, right? So there's a dangerous fire in the auditorium. I probably won't ask that one in the sense of. It puts people in a moral dilemma where one of the challenges of constructing a conductome, what we say, what we do, are two completely separate things. So in other words, if I said there was a fire in the auditorium and you go for the exit, but you find there's a person, struggling to get out, what would you do? Go back and help them, or keep running? Well, I'd toss the coin for that. But once again. A challenge is what people say and what people would do can be two completely different things. So what I want to get at here is only the thing about how we make decisions. Is it predictable or not? And in certain circumstances, it's extremely predictable, and in other circumstances, it's not. What differentiates those? What I want to basically push that onto is the idea of what is predictable from the following point of view. Now, this is more for the young people, students, or whatever. For others, we kind of the point or return to some extent. But this is what I want to do. What's a prediction model for who will be obese in 20 to 30 years? Who among you will be diabetic in 30 to 40 years, or 10 to 20 actually, depending on our age? And who's going to be dead before they get to 70 due to bad health? Basically bad lifestyle in this context. So these are incredibly important questions from a public health view, but they're absolutely all to do with decision making, right? So in other words, it's the decisions we make in a particular environment that lead to one or more of these. So these are all states that result from our decision making. Now, the thing is that we normally think of ourselves as having free will. And the question is that where on the spectrum of decision-making does free will, if at all, come in? Obviously, in E. coli, you can't really discuss the concept of free will, although you can discuss the concept of different alternatives in its behavior and how natural selection would act on those different behaviors according to the environment. But really, what I believe is that 99.99% of everything that we do, we basically automata, right? I mean, obviously, an example was if a ball in a gravitational field, or a cat in a gravitational field, or a human being in a gravitational field, the gravity all falls according to exactly the same trajectory. Basically, the cat will do that. The human being, I don't know, will probably try to think about all the wonderful things that happened in their life before they hit the ground, or think of a mother, or something like that. So the question is why do we make bad decisions in the sense of this thing about alternatives? Alternatives exist as possibilities, but how do you say, hey, I have a choice in some sense of which of those alternatives I go along? Because the thing is that here is a clear example where I don't have an alternative. You drop, and that's the end of it, right? Okay, so the thing is that one thing, being a physicist, as quite a few people who know me well now, I had a St. Paul on the road to Damascus experience where I think physics offers very few useful paradigms for complex adaptive systems. I might even go to say, if I probably in argument with Max, say none, and just use that as a point of discussion. But why do I say that? Well, the thing is that basically physics is based on the concept that the world is a machine. That has never ever changed, ever since Galileo, Newton, etc., etc. Before that, probably Kepler, and basically started to put forward the world as a machine. And the thing is that if we ask ourselves, how do we model machines? That's the fundamental framework in which we model machines. It's called differential equations, right? But with differential equations, it's like I said, a ball or a cat or a human being, we're all slaves to that law, right? You cannot avoid those laws. And there are no exceptions, right? Not one. That's the wonderful thing about physics. Once again, we are slaves to that law. But the difference between complex and simple systems, here I'm putting it in terms of the difference between being and doing in the following sense. That if we wanted to say what the difference between a cat and a ball is, and what we're thinking of the ball is, it's the cat after I crush it up into, obviously this is a thought experiment, not an actual thing we want to do in practice. But imagine we took all the molecules of the cat and we pushed them into made them into a nice ball, and then we just dropped the cat and the ball. Then the thing is that I would say we have two different points of view to that. One is the mechanistic, and the other is the adaptive. The cat obeys exactly the same laws of physics as the ball, but the cat does something extremely interesting. It's basically falls on its feet, and once again, natural selection has acted on the evolutionary history of the cat to do that. So in other words, basically what's happened with living systems is that instead of the laws of physics being an explanation for what a system does, they just become restrictions. And in no way do they explain at all what's happening to the system. We have to look beyond physics for that. And the other key thing there is the idea of a differential equation. What we should think of as a differential equation is exactly the following: that we can have all sorts of different configurations of a system, but we all follow the same rule for what the next configuration is at some other time step. The whole point of a complex adaptive system is essentially there's not one rule. There's multiple rules essentially for telling us what the next state of the system can be. They're called behaviors, right? So in other words, you can adopt different behaviors to basically go to different. So keep track of me, Max, in the sense of if I get to like. So basically, the evolution of functions is that's my little philosophy there, right? The evolution of function is the revolution that allowed systems to escape the tyranny of the laws of physics. So basically, every living thing is a data miner. So in other words, every living thing is basically taking in information from the environment, basically processing it and turning it into a decision, an action, and then you can basically link correlated combinations between environment and action as behavior, right? The only difference in some sense, let's call it between, let's data mining in the sense of artificial intelligence and data mining in living systems is just what the different substrates are and the different processing systems. Okay, so basically what I just wanted to say briefly here is that from the idea of complexity science, of just the sciences of complexity, anything that's to do not with physics. Why we're living in an incredibly interesting age and also incredibly depressing for a reason I'll say in a second is this. It's the data revolution. Basically, there's been a revolution in a generation of data. And why is it incredibly worrying? It's incredibly worrying for the following reason. You can Google, how much information can the brain hold, et cetera, you'll kind of get 10 to about 100 terabytes. All the books in the world is about 30 to 50 terabytes. And what are we generating per year? About 1 zettabyte, which is 10 to the 21 bytes. Basically, what that tells us is that we're literally drowning in data, right? So the vast majority of this data, that 1 zettabyte, nobody's looking at, and nobody can look at it in one sense. And the thing is that this is something extraordinarily new in human history. The point would be, if you think of books, there's never ever been a book, except maybe in the Library of Babel, whereby somebody's not looked at it, even if it was just the author themselves, or their mother, or close friend, or wife, or something like that. There always has been an interaction between an information set and somebody basically extracting information from that information set. Now, forget it. You know, basically within that 1 zettabyte, there's the possibility of saving lives, improving the planet, et cetera, We have no capability, or a very, very small capability, of really making progress with that. We're looking at an ever-decreasing set of information that is extractable from that expanding universe. Okay. So the thing is that when we talk about decision making, there's 3 important aspects, right? First of all, what is the goal or purpose of the decision? If we think of evolutionary theory, you know, the end thing is, are there more of me in the next generation, let's call it, right? That's the fundamental arbiter. Obviously, in human decision making, day by day, well, you know, how do I determine a metric of success? And the complication there is that, once again, if you think of going towards thinking about obesity, if I have a really delicious hamburger, piece of cheesecake or something like that with 1,500 calories, then the thing is that success could be there. There's just, hey, I really enjoyed that. If your metric of success is to do with, I want to stay healthy for the next 20 years, then they could be quite contradictory one to the other. But that depends on the behavior as opposed to the actual decision. Meaning, hey, if you have it once and once a month or something like that versus every single meal, there's obviously a huge difference between those behaviors and how they interact with the environment. Okay, so the thing is that what I've been trying to push is just the idea of the existence of this thing that I'll call the conductome. And basically what it is just saying, I want to come up with mathematical models that basically give me the probability for a particular behavior or a particular action. Proxy for that, a particular state, like your actual weight or something like that, as a function of what? Everything, right? So, because I have no idea what is relevant for bad or good decision making in terms of obesity and what is irrelevant. And I think one of the problems that we have in some sense in science is first disciplinarity, in the sense of these are the variables that interest me, the genetic part, these SNPs associated with susceptibility to obesity, or I'm looking at the social aspects of obesity, or I'm looking at the physiological aspects, or I'm looking at the psychological aspects, et cetera, and we still have a huge amount of, let's call it verticality there in terms of how we construct this, because basically, I'm not sure that there's anything from the point of view of at least variable classes that's not relevant to our decision taking in terms of the causes of obesity. Okay, so the thing is that a key question there is how much information do we need to make a good or a bad decision? Because within this is the probability for taking an action, that decision given this. The point would be is that within this, there might be variables that exist for one person and don't exist for the other, or they're completely different weights. You know, one of the things that, for instance, we come across, if had some blood test and the doctor says you've got hypertriglyceridemia, what's the emotional reaction? Well, that's going to depend very much on your educational background. But what that means is that things like that can have very, very different weights in this overall function for basically indicating whether you're going to change your behavior, whether you're going to, whether you can understand that, et cetera, et cetera. No, I'm not assuming anything. All I'm just saying is that I want to say, hey, what's the probability that this person did this as a function of some of the variables I have access to from the studies that we've done? No. But the thing is that there's no decision without information. We're not random networks. Right? A decision is always, it's just that you might not be explicitly aware of what goes on in the background, right? That's the key, right? I mean, so that's the thing. If you're thinking of a decision like, well, I've given this a lot of thought now and I've come to this conclusion. No, that's not how the brain works. It's basically you do something, you take an action, and I guarantee there's a causal path from many factors, that's what this conductome is, to taking that action. Then often what happens is that if you want to think along the terms of why did I take that decision, then the point is that there's often a posterior rationalization to try and justify why you took that decision. But that's not necessarily, why you took that decision really, as we'll see. Okay. So in that sense, this idea of constructing this conductome, one of the key challenges we face is there is a big difference between the human being's way of constructing this internally and whether it represents reality or perception. One of the key things there is that basically our decision-making process is a representation of a perceived world and not the real world. And as we'll see, that is a huge potential driver for obesity, meaning, hey, the way we perceive the world in the sense of or perceive ourselves is very different than the way the world really is. What that's basically saying is that our predictive models can be biased for one reason or another, right? And we'll see some of an example of that bias. An algorithmic representation of that decision-making process, I mean, that's basically what I'm trying to do, is to construct, let's call it machine learning models that try to represent that thing that's associated with what's going on inside your head, as it were. And that first thing I showed in the sense of the 42 is at least one model that's basically a meta model associated because its output is associated with the decision-making processes of all the people, the 1,076 that were basically answering all those questions, etc. And there's an implicit footprint of the decisions that they've made in questions. That's just one of the huge challenges, is that what is the direct, or what is the map between and the other. Okay, so we'll skip that. So basically, your decision-making process depends on who you are. In that sense, we can think of genetics as a good representative of that. What and how you think, and what and how you feel. And basically, those three together essentially determine what my prediction, decision, or heuristic or algorithm is, and that is basically what determines my behavior. Okay. So another thing is that turning that concept of the conductome to the question of obesity, we can argue in some sense, and this is something for the workshop that I'm organizing tomorrow and Friday, there's going to be, I hope, a key theme in the sense of nature versus nurture in some sense. I don't have time to go into it now, but what's absolutely clear is that basically obesity is a disease that's associated with decisions. So in other words, thinking of a decision as an action that's basically looking at what we do within a certain environment. So the thing is that what I want to do is take some particular dimensions that we know are important in terms of behavior. One of them is consumption, right? And basically, what I'm showing here is that one of the first things we did was to look at one of the large epidemiological surveys that they carry out in Mexico, called Ensanut. And the thing is that they ask people questions up to, how many portions of cornflakes do you eat in a week? And the thing is, it's extremely useful. Obviously, it's self-reported for being able to try and determine what people consume. So basically what this is a graph of BMI as a function of age for these over 20,000 people. And this is basically what they eat, their self-reported consumption in terms of total calories, where we put in a cutoff at 5,000 calories and 500 calories, thinking, well, that's not very sensible above or below that. So the thing is that obviously, the R squared for these sort of, yeah, Philippe. The data, it's Ensanut. It's a national survey that's representational of the Mexican population, where they go to people's houses and they'll put this big questionnaire and they'll take anthropometric measurements, et cetera, et cetera. It's all of Mexico, yeah. So basically what we see here is that underlying that huge statistical variance, there's an incredible, the F statistic for this is about 300, or 300 or 400. There's something incredibly statistically significant underlying that tendency. And what it is, it's a really lovely parabola, right? So in other words, what we're saying is that the age groups we're looking at between 20 and 80, people get heavier, 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 and then they get lighter, 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 right? And what we see here is that people are eating less and less and less and less and less as a function of age. This is also extremely statistically significant. The unfortunate thing is how much less on average are people eating, these 20-odd thousand people per year, 8 calories, right? So here and here, that's 60 times about 8 calories. That's about 480 calories. That's a substantial fraction of our daily diet that you're changing in age 80. But if you're trying to say, hey, can I really understand people's eating habits and eating behaviors? This is, I don't like the word emergence very often, but what I would say is this is a truly emergent phenomena, meaning at the population level, this is telling us that the differences are incredibly, incredibly small, even though differences at an individual level might be absolutely huge. Basically, the standard deviation for calories ingested is about 1,300 calories. 8 calories a year is what you call small compared to that. So the thing is that key thing here, though, from the point of view of the conductome, is the idea of this is not noise, right? The thing is that within, if I think of the 2,500 variables, well, here's one variable that gives me some interesting statistical result. But the point would be is that it's not one underlying statistical result with a huge amount of noise. Within this is that, for instance, Michael Phelps would be up here at 12,000 calories. And if some other person, normal person who wasn't a Michael Phelps was consuming 12,000 calories, so Michael Phelps, in the sense of the BMI curve, would be down here, and somebody else who was consuming 12,000 calories would be up here. So the thing is that what do these two graphs tell us? They tell us the following thing. So here, there's a population-wide equilibrium point. Basically, it's at about age 50, 52. And the thing is that what we can imagine is that if I take that as the equilibrium point on the consumption curve, then the thing is that to this side, there's an excess of consumption. On this side, there's a deficit of consumption. And what we can do is basically look at the relationship between that excess and deficit and correlate it with the slope. So in other words, the rate of increase of BMI is a function of and the result of that regression, and it's a very statistically significant regression. Basically, what that's telling us is that there's a self-consistency, if you will, between this as being the motor of this, right? And moreover, this itself is telling us basically, so from age 20 to about age 30 and a bit, 35, basically 70% of all population weight increase is over that interval. Basically what he's saying is that if you don't get the people, 10 minutes, if you don't get the people here, you're in big problem, because basically once somebody's this high on the curve, it's very, very difficult to have a reversion. Okay. So the thing is that what we're seeing there is behavior translated into the proxy of consumption in the sense of total consumption. But within total consumption, there's a large set of other variables in the sense of it's not just a question of how much you consume, what is it that I'm consuming? And basically what I'm just showing here is that the mix of consumption changes as a function of age too, right? So in other words, it's not only that we're changing our decision-making with respect to total consumption, we change it with respect to the spectrum of things that we're consuming. In particular, some of those are very bad, meaning for protein consumption, there is a large decrease as a function of age, and that leads to why older people get into problems of fragility and loss of muscle mass. So the thing is that what I'm concentrating here is that I'm just going to look at two important subsets, let's call it, of the conductome by proxying, in the sense of one is consumption, the other is exercise. And basically, here what we kind of see is the obvious, in the sense that the more you exercise, the less the rate of obesity. But the point would be is that for these proxies of behavior, how much you consume, what you consume, how much exercise you're doing, what type of exercise, basically, if you look at this, what this is telling us that if you, this is basically diabetes, not obesity. If you walk as an exercise, you've got a much higher diabetes rate than actually not doing any exercise at all, right? Which I'm not recommending as a way of saying don't walk, it's dangerous. Basically, what's happening there is that there's a statistical bias, because people who've been diagnosed as diabetic, when they go to the doctor with symptoms of diabetes, it's likely that they're overweight, and the doctor's going to say, hey, please start to do some exercise. Well, what exercise are you going to do? But the thing is that what I want to get across here from the point of view of the challenges of the conductome is there are many studies that are going to say, here's my population, this is how much exercise. But the thing is that, for instance, total amount of exercise is just a proxy. That below it is there are literally hundreds of other variables that are characteristics of that exercise. Is it intense? Is it not intense? What type it is, et cetera, et cetera. And the thing is that the challenge is to get the data that respects all of those different characterizations. Once again, it's basically saying, how do I come up with a taxonomy, let's call it, of different behaviors? Exercise hard, exercise not hard, et cetera, et cetera. Okay, so there's sample evidence we eat too much of the wrong things, we don't exercise enough, and these are all associated with bad decisions. Why do we make those decisions? And the thing is, obviously, the question there is what's rational and what's not rational. But from the point of view of the conductome, there are three fundamental questions. What value function our decision making is based on, what prediction model we have, and what information set we have that goes into that prediction model. So apologies in Spanish. So for instance, one of the challenges of public health is like public health goes, exercise, don't eat that. And the point would be is that here, what we asked is like, how important do you think exercise is? And basically 99% of the population said it was very important or important. And the point would be is that the incidence of obesity was actually higher in those who said it was very important, as opposed to those who said it was just fairly important. Whereas when we look at, do you know what the BMI is that characterizes normal weight, 93% don't know, but the rate, the obesity frequency is twice as high in those who don't know versus the do know, right? So there's obviously, in terms of value function that goes into our prediction model, this is being a proxy for something that's much more important than this, right? So everybody knows don't drink Coke, everybody knows, hey, do some exercise, but it doesn't tell you anything about what people's behavior is. Okay. So back to the rationality or irrationality of the conductome, probably be the last part. One of the things that we do is to basically one of the things that we want to do with technology is just challenge or basically describe the difference between the perceived world and the real world. And one interesting dimension of that is to say, okay, what do you think you are on this scale in the sense of BMI? And then what we can also do is know where they are on that scale. And we can look at the deviation, and because that deviation is now a measure of the difference between your perceived world and the real world. And the thing is that what you can find is basically this is the deviation. What we're looking at is all the set of obese people, and that's these two figures here essentially. And what we can find is that the actual number or frequent or a percentage that identify themselves at this end is actually quite small, right? So in other words, the large majority are identifying themselves as further down the scale. Right? So if you're not aware of what your BMI is, then the thing is it's hardly likely you're going to take any steps to do something about it. Back to the idea of obesity versus education, basically you have a linearly decreasing incidence of obesity as a function of educational level. But the thing is that a large part of what our project is to go, okay, what differentiates this person from this person, from this person, from this person, from this person, from this person? And we have a large set of differentiators that tell us, hey, the behavior set of people here at this end is different than this end, which is different than this end. And one of the ones that's most interesting here, back to the idea of what's the deviation between your perception of your BMI and the real BMI, this is the difference between real and perceived in those categories. And this is how it changes as a function of educational level. What you find, particularly strongly for women, when it's basically zero here, what that's saying is that women with a postgraduate education, their identification of their own BMI is the same as their real BMI. Whereas here, basically, we're almost talking about a full category difference. For men, there's also a tendency, but it's less notable. And one of the reasons for that is that basically for men, well, there's a lot of evidence that shows that height is actually a big differentiator for social success, whereas for women it's more BMI. And the thing is that just to show why that this has a large impact, it's the idea here of one of the questions that's asked on the surveys, in the last year have you lost or gained weight? And was this weight loss intentional? What we're showing here is just that at the level of higher education here, basically 16% versus 4 to 6% at the low level of education are actually doing something about trying to lose weight. So once again, it's not just a question of, hey, the perception, it's a question of how you turn that into actions from the point of view of what to do about your weight. For the genetic part, we basically looked at about 772 SNPs, and the thing is that you can have a sub-predictive model, a sub-machine learning model just on the genetic part. The nice thing here, we can create multiple models on one part, another subset of data, and say, hey, where does most of my predictability come from? And on the genetic part, there's very low predictability. Now, the thing is that is probably to do with, like, you're not looking at the right things from the point of view of essentially, a large part of what we'll be doing in this workshop is trying to determine, well, basically what genetic substructures are more associated with behavior than just looking at a particular SNP that's associated with a physiological distortion. Okay, and then lastly, basically, I think it's clear that there's interesting things. I mean, it's been around for a long time, the idea of the thrifty gene, et cetera, et cetera, et cetera. one of the problems with the real world is there's only one of it. How do you test hypotheses like that? So one of the things we're doing is basically just trying to recreate the world of over 200,000 years ago in an agent-based simulation to say, hey, okay, if I look at a particular strategy, let's call it behavior, in the environment then, and now I put it in the environment now, what happens? So anyway, so to conclude, the human conductome is the entirety of factors which control human behavior. Obviously, it's extraordinarily multifactorial and adaptive, requires big, deep data across multiple scales to understand it. And we just don't have that data. But the thing is that this project that we've got here with this population, the idea is to bit by bit create the deepest database on the planet for these particular populations, in the sense of trying to span across all these different scales. A crucial ingredient of conductome is how we evaluate decisions, but the different concepts of value we need to obviously understand a lot better, in the sense of, why do you make the bad decision? It's because I'm not looking at 20 years in the future. I'm looking at whether I enjoy this now. And another crucial ingredient is understand how our mental model, individual mental model of the world, is different to the actual model of the real world, and to say, what can you do to make those two models? It's basically associated with the idea of behavior change, right? But once again, the deviations between them can have severe psychological, social, and other health consequences. So we kind of call this Project 42 for the reason I showed you at the beginning. Basically, you know, what we want is just to have collaborators to basically go basically implementing multiple protocols across multiple disciplines. You know, there's a lot of work to be done, and anybody who's interested is invited. And finally, this is a subset of people who, you know, I didn't do any of this on my own. We have a very large group that contributed to all of this, and all the work I presented is work with those guys, for whom I am very grateful. Thank you.
Thank you for the talk. So I had a question about the BMI. So as you know, it's a controversial index, or and so you took it as a way of quantifying some output behavior, I guess, and you have controlling parameters like the food intake and also age. So I wanted to know, how can you control for artifactual effect of a given formula like a BMI? Let's say now you don't take BMI, but you take also the, they said that's something that works maybe better is to take the, how wide your waist is, for instance, not include the BMI. Maybe you're going to take another curve and it's going to change maybe the picture of,
no, you know. It doesn't.
So I wanted to know, is there, so you see you have almost a kind of social perception that what obesity is. Then we try to quantify that by some kind of index like BMI. But what's the, is there a way of controlling for the artificial, or maybe not, but addition of some formula versus others?
No, I mean, the thing is that I can create the same model for waste, and it'll be a parabola. So in other words, there's, oh yeah, I mean, there's a 90% correlation between waist circumference and, I mean, it's the old thing of like, hey, you have some American football player who's got who's obese, but he's very muscular, right? But the point would be is that there's no perfect measurement, right? They're all different complementary observable. So we looked at waist to height. The trouble with waist on its own is like, well, if you're just taller, you're going to have a bigger waist, all else being equal, right? BMI in that sense is kind of nice because it's kind of something that scales, right? So in other words, you're taller, you're going to weigh more, right? So the thing is that it's trying to take that into account, to, you know, modify or go with deviations from that sort of relationship, whereas waist doesn't. But there's multiple. And the point would be is that each one can be telling you something slightly different. But the point would be is that BMI is absolutely no way perfect. But in terms of capturing, what consumption or what behavior does to you, or exercise, it's one among several, but it's a good one. But it's not perfect. But you won't find any real significant differences, right? You'll find these outliers where, hey, somebody's high BMI, but they don't have much fat content or something like that, yeah? Absolutely, absolutely, yeah, yeah.
Thank you for your talk, Chris. Hope you can hear me. I have a technical question.
Yeah.
How do you handle mixed data types? I assume your data is numerical, categorical, and I noticed that your first slide you used naive Bayes classifier. Have you considered other methods, random forest perhaps, that can handle multiple different data types?
The problem is that, how to put it, for many years I've been like a machine learning, artificial intelligence guy, but luckily coming from a physics background, I couldn't care less, right? The algorithm really doesn't matter, right? So in other words, the importance of extracting the right information and the right questions to ask is far more important than getting an extra % on your predictability. And the other thing is that what you really need is to have an analysis that's transparent. Right? So the point would be is that if you go into a more, it's why I don't believe in deep learning other than when you couldn't care less why it gives the answer, right? Because what I care about is to be able to deep dive on trying to understand why.
Right. So in that vein, you want the interpretability. Have you considered probabilistic graphical models, Bayesian networks?
No, I mean, Bayesian networks in an ideal world would be the best way to try and go about things because they're a much better, potentially a much better representation of causal relationships. But they're very, very fragile with respect to your data in the sense of how it can come out. But once again, in an ideal world, it's something I'd like to be. But of all, in other words, I don't think if I threw Bayesian networks on this, I'd go, now I see everything, right? That just wouldn't happen. But in principle, it's something definitely a framework to use.
Thank you.
Okay, I think that we're a little bit over time, so if you have more questions, I invite you to ask those in the coffee break. And please, let's come back at 12 for the next talk. And thanks the speaker again.